Usually when we talk about clinical medicine, there is this expectation of total precision. It feels almost like engineering, right? A patient comes into the ER, you take an X-ray, it shows a jagged white line on the femur, and the doctor just points and says, there it is, broken bone. It's clean, it's just a binary reality.
Right, yeah. We really like things to be visible. There's a lot of comfort in just being able to point to the problem on a physical screen.
But then you step into the world of biomedical research and data analysis, and, well, suddenly that crisp X-ray machine is replaced by a spreadsheet, like 10,000 rows of raw, unformatted numbers. And looking at that, it's murky. I mean, to me, it just looks like TV static.
Oh, totally. It is the absolute definition of diagnostic muddy waters. Those numbers are entirely meaningless until you give them a logical structure. And frankly, that is exactly where a lot of researchers just freeze up. They see the math and panic.
Which is exactly why we're tackling this today. For those of you gearing up to Master Lecture 18 on the overview of data analysis, those exam concepts can look like this terrifying wall of math. But today on this deep dive, we aren't just going to memorize an answer key.
No, definitely not.
Right. We are going to decode the logical story behind this material. If you understand the actual flow of how data is handled in the real world, the exam essentially answers itself. You'll be able to speak the language of data fluently. So, here are the ground rules for today. We're going to conquer the multiple choice questions provided in the source material, specifically questions 1 through 26. I'll read the question number, the prompt, and the options, and then you'll jump in to reveal the correct answer and explain the core concept. Sound good?
Sounds perfect. And I love how you framed it. Data analysis is literally just a narrative. And like any good narrative, it has a very specific chronological sequence.
Awesome. Let's start right at the beginning of that narrative. Section 1, the blueprint. When you are setting out to analyze your data, what is actually driving your plan? I'm looking at question 9 and question 13 here. They both basically ask, an analysis plan depends on what? And the options are A, objectives of the study or study type, B, budget, or C, availability of statistician or time.
Yeah, so it is incredibly tempting to let logistics take the wheel, but the only correct answer here is A, objectives of the study type. Your analysis plan must be strictly driven by your research question.
Because budget and statisticians are just logistics.
Exactly. Science dictates the math, not the wallet. If you change your statistical approach simply because you're short on time, you're compromising the integrity of the whole research. The objective is your absolute North Star.
Okay, so the objective sets the destination. But how do we actually get there? Question 6 asks for the sequence of data analysis strategy. The options are just a jumbled list of 7 steps, labeled A through G. Can you walk us through the logical flow?
Gladly. The correct answer for the sequence is C, D, B, C, F, E, G, A.
Okay, wait, let's translate that alphabet soup into actual steps. Say we want to study the link between drinking coffee and heart palpitations. What is step 1?
Right, sorry. Step 1, which correlates to D, is identifying your study type. Are we just taking a snapshot of people today, or are we following them for 10 years? Once we know the framework, step 2, or B, is identifying the main variables.
So in our scenario, the variables would be like cups of coffee per day and resting heart rate.
Precisely. Then step 3, which is C, is getting familiar with your data. This is where you check for consistency, you hunt down duplicates, and deal with missing values. If someone wrote down that they drink 400 cups of coffee a day, you need to catch that impossible outlier right away.
You have to make sure your raw materials aren't defective.
Exactly. Which leads to step 4, F, characterizing the study population. Before you look at the coffee, who are these people? What's their baseline age, gender breakdown, general health? You examine the baseline first. Only after you know your population do you move to step 5, E, which is examining the actual association between the exposure, the coffee, and the outcome, the palpitations.
This makes so much sense when you layer it out like this. You don't just jump straight to the finish line.
You really can't. If you find a connection in step 5, then you move to step 6, G, creating additional two-way tables. This is where you might stratify the data to see if the coffee effect is different in men versus women. And finally, step 7, A, is conducting advanced analysis.
Like complex regression models to account for diet, sleep, and stress all at once.
You got it.
Okay, so just to cement this for you listening, question 25 asks basically the same thing. Correct sequence in the steps of data analysis, and gives options like identifying variables, checking consistency, examining baseline, examining association. So based on what you just said, the answer has to be B, I, 2, 4, 3, which perfectly mirrors those 7 steps.
Yep, it maps perfectly. It's a rigid sequence for a reason.
It's basically like building a house. You know, you don't pick the paint colors, the advanced analysis before you've laid the foundation and checked the data consistency.
That is a great analogy.
So let's group these steps into bigger buckets. This brings us to question 1, which asks, the 3 stages of data analysis are in the following order.
Right, so the answer there is B, recoding stage, descriptive stage, and analytical stage. You clean and prep the data in recoding, then you look at what you have in descriptive, and then you test for relationships in the analytical stage.
That perfectly answers question 19 as well, which mixes up multivariate analysis, recoding, measures of association, and frequency distribution. The correct sequence is C253I, which maps exactly to recode, describe, analyze.
Exactly.
But wait, let me push back a little here. Why is recoding its own massive stage? Like, why can't we just use the raw data? Well, think about exact birth dates. If you collected raw birth dates from 1,000 people, analyzing hundreds of unique dates is just chaotic noise. Recoding translates those messy raw inputs into usable categories, like age groups under 18, over 35, and so on.
Oh, I see. So it's prepping the ingredients before you cook, which helps answer question 14. At the time of data cleaning, which of the following is not done? Options are removing duplicates, missing observations, calculating strength of association, checking range.
Yeah, that would be calculating strength of association. Because calculating association belongs in the analytical stage, definitely not the cleaning or recoding stage.
Makes total sense. So moving to the descriptive stage, question 15 asks how to describe population characteristics. And question 21 asks what is accepted from describing a study population.
For describing characteristics in question 15, the answer is A. Calculate the frequency distribution. You're essentially just taking a highly detailed head count. How many men, how many women, you know.
Right. And for what is accepted in question 21, the answer is D. Conduct logistic regression analysis. Because again, regression belongs to the analytical stage.
Okay, and just to drive the nail home, question 26 asks, which of the following is not done during the analytic stage?
That is A. Calculating frequency of the outcome in one group. Frequencies are strictly descriptive. You aren't testing anything yet.
Okay, so having clearly separated the descriptive and analytical stages, let's zoom strictly into the final, most complex phase, the analytical stage. Question 24 is a true or false. Hypothesis testing is conducted in an analytical epidemiological study.
The answer is A. True. Testing hypotheses is the defining feature of analytical work. The moment you ask, does X cause Y, you are in the analytical stage.
Even within that stage, there's a progression, right? Question 5 asks, in analytical stage of data analysis, we perform the following in order, and it mixes up univariate, multivariate, and stratified.
Right. The correct order is B, univariate analysis, stratified analysis, and multivariate analysis. You have to build up the complexity gradually.
So, question 3 and question 11 both basically ask if multivariate or logistic regression models are used during the descriptive stage.
And for both, the answer is absolutely B, false.
I need a simple way to remember that univariate to stratified to multivariate order. How about this, a detective analogy?
Oh, I like those. Let's hear it.
So univariate is interrogating one single suspect in a room, just one-on-one. Stratified is when you realize there are gang dynamics, so you group your suspects by neighborhood, you're layering the data.
I follow you.
And then multivariate is that crazy red string conspiracy board on the detective's wall, connecting all the suspects, motives, and alibis together to find the true cause.
That is brilliant. Yes, you can't jump straight to the red string board on day one, or you're just flying blind. You have to build up to it.
Okay, the detective board is set up, but different crimes require different investigative techniques. Let's talk about matching the study design to the question. This feels like a high-yield exam section.
It really is. The physical reality of the disease actually dictates the math you're allowed to use.
Let's test that. Question 7. In case of descriptive studies, which of the following is wrong?
The wrong statement is B. We compare the study outcome for two groups. I can't emphasize this enough. Descriptive studies never compare groups. They only look at one group.
Okay, what about question 16? While examining association, based on a priori hypotheses, we compare frequency of exposures between cases and controls using appropriate measure of association, true or false.
That is a true. That is the core of analytical studies.
So let's get into the specifics. Question 17 gives us an analytical study, acute nature, and a frequent condition, and asks us to match it to a measure.
Because the condition is frequent, time is on your side. You can follow healthy people forward in time. That makes it a cohort study relative risk.
Wait, let's clarify that for the listeners. Why does frequent mean we can go forward?
Well, if a disease happens often, you can afford to gather a group of healthy people expose some to a variable, and just wait and watch. You know exactly how many people could have gotten sick, the denominator, so you can calculate true, literal risk.
Okay, but what if it's rare? Question 8 and question 22 both ask about an analytical study, acute nature, and rare condition.
Right, if a disease affects 1 in a million people, you can't follow healthy people forward. You'd wait decades and never see a single case. You have to work backward by finding people who are already sick.
Ah, so you artificially pick cases and control.
Exactly. And because you artificially manipulated the group sizes, you destroy the natural denominator. You literally cannot calculate true risk. You can only calculate odds. So the answer for both Q8 and Q22 is case control study odds ratio. Note that for Q8 it's option B, and for Q22 it's option A, but the text is the same.
That is such a crucial conceptual difference. Forward equals cohort equals risk. Backward equals case control equals odds.
You nailed it.
Awesome. And question 23 is a true or false. Prevalence ratio is one of the measures of association calculated in an analytical cross-sectional study.
Yeah, true. Cross-sectional is just a snapshot of right now, so you measure prevalence.
Okay, so we've got the theory down. Let's shift to section 5, the tools of the trade and the pitfalls to avoid. Question 4 and question 12 focus on software, specifically EpiInfo. Is it used for data entry and analysis and creating data collection formats?
Yes, the answer for both Q4 and Q12 is A, true. It's a specialized software that handles rigorous data safely.
Which contrasts with standard spreadsheets. Question 10 asks if the use of Excel or spreadsheets should be avoided, and question 20 asks if spreadsheets are ideal tools.
Right, so for Q10, Excel should be avoided is A, true. And for Q20, spreadsheets are ideal tools is B, false.
Wait, really? Why is Excel so dangerous? People use it for everything.
They do, but standard spreadsheets lack strict audit trails. It is incredibly easy to accidentally highlight and sort just one single column instead of the entire sheet. If you do that, you instantly scramble every single patient's data, one misclick, and you invalidate a year of research.
Oh, wow. That is terrifying. Okay, so use specialized tools. Now, what about the human errors? Question 2 asks what to avoid while performing data analysis. Options include post hoc analysis and data drenching.
You want to avoid both, so the answer is D, A, and B.
And question 18 asks for the correct statement among options regarding data handling.
The correct statement is B. Recoding can be done for key variables. The other options essentially promote data drenching, which is unacceptable.
Okay, let me stop you there. Data drenching sounds like a weird scientific spa treatment. What actually is post hoc analysis and data drenching in everyday terms?
In simple terms, it's fishing for coincidences. A rigorous scientist states their hypothesis beforehand, but a bad scientist, one engaging in data drenching, runs the analysis, finds no connection, and refuses to accept it.
So they just keep testing random stuff.
Exactly. They start running hundreds of random, unplanned statistical tests on their data, hoping to find any two variables that correlate, like testing coffee against shoe size. The math guarantees that if you run enough random tests, eventually you'll find a connection just by pure chance. But it's totally meaningless.
Oh, so post hoc analysis is basically changing the target after you've already fired the arrow.
Precisely. It's fundamentally bad science.
Man, that really ties everything together. So just to recap the whole journey for you listening, we started by establishing that your analysis plan is a strict 7-step blueprint driven entirely by your objective, not your budget. Then we separated the 3 massive stages. You recode to clean the data, you describe it by taking a head count, never comparing groups, and then you analyze it.
Right, and in that analytical stage, you build up slowly, univariate stratified to multivariate.
The red string detective board. And then you have to map the math to the reality of the condition. Forward-looking cohort studies for frequent events to find risk, and backward-looking case control studies for rare events to find odds. And finally, toss out Excel to avoid silent errors and the ultimate sin of data drenching.
That is a perfect summary. If you can visualize that flow, from the moment the raw data is collected to the final equation, the logical story just clicks into place. You really don't need to memorize isolated facts anymore.
But, before we wrap up, I want to leave you with the provocative thought. We just talked about how easy it is for a frustrated researcher to accidentally go fishing for coincidences, that data drenching if they lose their discipline.
Right.
Well, right now we're seeing this massive explosion of automated AI data analysis tools. So do you think these AI systems will be our saviors, strictly enforcing our analysis plans and preventing us from running rogue post hoc tests? Or because an AI can run a million statistical correlations in a fraction of a second, will it actually make it easier than ever to accidentally uncover random, meaningless coincidences and disguise them as breakthrough science?
Wow. That is a phenomenal and honestly somewhat unsettling question. How does the role of the researcher change when the software does the thinking?
Exactly. It's something to carry with you as you move from studying these concepts to actually conducting modern research. Remember, raw data isn't a clean X-ray. It's a murky sea of static. Your analysis plan and your discipline in sticking to it is the absolute only way you pull the truth out of it. Keep digging, keep questioning, and good luck mastering the logic of data.